Today we're going to look at the usefulness and dangers of using radioactive sources. The first aim is to describe how radiation can be harmful, then explain how we can protect ourselves from radiation, and finally we'll explain different uses of radioactive sources. I'm going to start off with a photograph today, and it's a very interesting photograph. Let's zoom in. Here is a picture of some of the greatest minds in physics. It was taken at a physics conference, and you may notice some familiar faces, for example, Albert Einstein over here. But what I find particularly interesting about this photo is there is only one female, whether you spotted her or not, here she is. And this highlights one of the greatest issues in physics, is that it's a male-dominated science at present. This, however, is unquestionably one of the most important figures in physics and chemistry. This is Mary Curie. Mary Curie was the first woman to win a Nobel Prize. She is currently the only woman who, I believe, has been awarded 2 Nobel Prizes, and she was the first female to be employed as a professor in the University of Paris. But why is she famous? Well, firstly, she actually coined the term radioactivity. Before her, there was no radioactivity. She's discovered 2 very important radioactive elements, polonium and radium. And her understanding of radioactivity helped us develop nuclear medicine, such as radiotherapy. Sadly, Mary Curie died due to exposure to radioactive sources she worked with. She famously used to carry test tubes of radium in her jacket pocket while she worked, as well as working closely with X-rays. You see, the dangers of radioactivity hadn't truly been discovered around this time. In fact, when radium was first discovered, we noticed it glowed in the dark. This seemed like a magical property to people, and some people confused this glow-in-the-dark sort of life force to be some sort of life-extending miracle substance. So for a while, people went radium mad. They put it in chocolate, they put it in water, they put it in toothpaste, they put it in makeup, they put it in children's toys. They used it as a treatment for impotence, like an early form of Viagra. And they used it to heal back pains by applying it to pads which they put on people's backs. Most famously, radium was used to paint the needles or the hands of clocks so they would glow in the dark. Allegedly, some of the females who worked in these factories used to, as a joke, paint their teeth using the radium paint, and so when they'd go home and switch the lights off, they'd smile at their husbands and show their glow-in-the-dark teeth. What people didn't realise was how lethal radium was. And it wasn't until some of these actions resulted in the development of cancer in some humans that we started taking it seriously. So this is one rare case where I would say it's not always a good idea to eat your greens. So we know that alpha particles, beta particles and gamma rays are ionizing. They can strip electrons off atoms and cause them to become charged ions. And if you remember, alpha particles, well, they're stopped by paper and skin, so they can't get inside your body. So alpha radiation is actually harmless outside our body, but when it's inside, it is the most dangerous radiation. It can cause extreme damage in localized areas. For example, if inhaled, it will cause extreme damage to soft lung tissue. Beta and gamma are more penetrating. Beta gets some way into the body, it can pass through, and gamma can easily pass through due to its small size. Gamma, even though the most energetic, because it's so small, it's less dangerous because most of it will pass through the body. Same with beta. In high doses, these radiations kill cells and tissues, which can lead to radiation sickness. In low doses, it can damage DNA, cause cells to mutate, which can result in cancer. The dose depends on 2 things: how long you're exposed to the radiation. The longer you're exposed to it, the higher the dose, and the energy and penetration power of these radiations. For example, gamma radiation carries the most energy and is the most penetrating. So if your cells were exposed to gamma radiation for a long period of time, you'd receive an incredibly high dose of radiation. So now we can describe how radiation can be harmful. And because it can be harmful, we need to protect ourselves against it when we are handling radiation or radioactive sources. In a school lab, you may have seen your science teacher demo certain radioactive sources, and there's certain rules you must follow. Firstly, avoid skin contact at all times. Use tongs to handle the radioactive source. Keep it away at an arm's length. Point it away from you. Do not look at it directly. Store it in a lead-lined box, and obviously minimize your exposure time wherever possible. The radioactive sources we use in school are generally quite weak, but they can cause damage. After all, they are all sources of ionizing radiation. However, some people work with radiation all day long. If you work in a nuclear power plant, you'd have to take more extreme measures. For example, you'd have to wear a full protective suit, such as this one. This ensures that no radioactive particles can be inhaled, nothing can get under your fingernails, and obviously into your body. The suits can be lead-lined to further prevent, for example, gamma getting through. Often they work with lead and concrete barriers between them and the source. Once again, lead and concrete stops gamma getting through. We use thick lead screens, again, to block gamma sources of radiation. Remember, alpha can be easily blocked and beta won't penetrate too far, but gamma will easily get through things, so you need thick lead. Rather than handling the sources directly, we use remote-controlled robot arms to handle the sources. The key message here is avoid any sort of skin contact and distance yourself as far as possible from the radioactive source. And that's how we explain how we can protect ourselves from radiation. So now let's look at some uses of radiation. You actually have radioactive sources in your house. If you opened up your smoke alarm, you'd find an alpha source in there. Now, alpha is quite safe in the home because it only travels about 2 centimeters in air before it gets blocked, and obviously it can't penetrate your skin. So we'd never use beta or gamma in here because it'd be too dangerous. It would easily get through our bodies and cause potential damage. So with a smoke alarm, a weak alpha source is used, which is here. And what happens is this alpha radiation is used to ionize air particles to create a flow of current. So here's an air particle, and when the alpha source goes near the air particle, it strips off electrons, causing it to become a positively charged ion. Now essentially this is a circuit with a positive electrode and a negative electrode. So now the ion's charged, it will be attracted to the negative electrode and transfer electrons, so you get a flow of current around this circuit as this continually happens. The key point here is while there's a current flowing, the bell doesn't ring, the alarm is silent. Now let's introduce a source of smoke. Smoke will absorb alpha particles. So if our smoke particles basically get into the system here, the alpha particles will get absorbed by the smoke, and therefore there'll be nothing to ionize the air particles. As a result, they don't become charged. As a result, a current doesn't flow, and as a result, the alarm rings. We can use gamma radiation to sterilize food and surgical equipment. Basically, we put our food in something like a microwave oven, but it emits gamma radiation, and it will be blasted with gamma radiation, killing any microbes on the food, for example, bacteria, harmful fungi, cells, and so on. And you could apply exactly the same logic to surgical equipment as well. Now, traditionally, we used high temperatures to sterilize such things, but there's a problem with that. High temperatures will melt plastic equipment, and obviously they'll start to cook food and damage food as well. So use strong gamma source to kill microbes. It has to be strong because you are trying to kill cells, living cells. You use a source with a long half-life, and that means you don't have to replace it as frequently. And obviously if you're not replacing it as frequently, you're not exposing yourself to that radiation as much. And it avoids the need for high temperatures, so food and plastic isn't damaged. Because gamma radiation in very high doses is very damaging to cells and tissues, we can use gamma radiation to destroy cancerous cells. Gamma kills all living cells in high doses. So if we target cancerous cells, we can actually start to kill them. Unfortunately, it's very difficult to just target cancer cells, so we must minimize damage to healthy tissue. Because the more exposure you have to radiation, the more healthy tissue that's damaged, you'll start to develop radiation sickness. Traces are another use of radioactive sources. We can use beta and gamma to diagnose specific medical conditions like the presence of a tumour in your body. How this works is first you inject a source into a patient. So you'd get a radioactive source and you would literally inject it into someone's body. This source then travels around the body, let's say using the circulatory system. And depending on what source and what type of isotope you've used, it will accumulate in certain regions in the body. You then use an external detector to detect the radiation. So it will basically, you scan the body and it will detect the radiation where it's coming through. That sensor is attached to a computer which will produce an image on a screen so you can take a look at what's going on inside the body. It's very important that we use beta and gamma because they will pass through the body. If it was an alpha source, it would cause incredibly high amounts of local damage. Also, it's important that these sources have a very short half-life because you don't want them to stay radioactive for very long if they're entering our body. We can also use gamma, and it has to be gamma, not beta or alpha, to detect leaks in underground pipes. So here I've got a pipe which is underground, it's got a crack in it and something's leaking out. What you do is inject your gamma source here and the gamma will basically radiate outwards. You see, beta wouldn't get very far and wouldn't be able to emerge from the surface, alpha wouldn't get through the pipe itself. In fact, there's a good chance beta wouldn't get through the pipe itself. But gamma will get through because it's so small, it's just an electromagnetic wave. So what we can do is use a detector above ground, and where it detects the highest readings of radiation, you can assume that's where the crack is. And finally, and quite strangely, we can actually use radiation to measure the thickness of paper as it's being rolled out. If you've ever noticed, paper comes in one standard thickness when you buy it in a pack. So how does this work? Well, firstly, we have to use a beta source, and you'll understand why in a second. So the beta source will emit electrons or high-speed electrons because that's what beta particles are, and they'll be picked up by a detector on the other side. Now, as the paper rolls through, some of the paper will be thicker, and that will reduce the amount of beta radiation that's being received by the detector. And sometimes that paper will be thinner, and that will allow more beta particles through to the detector, so the readings will vary. Alpha wouldn't get through at all, so wouldn't be picked up by the detector, and gamma would get through so easily that they would get no variation in the reading because it would just all get through the paper. So if the paper's too thick, the reading will be low. If the paper's too thin, the reading will be high. And the rollers are adjusted accordingly to put more pressure on the paper or less to make sure it's of an even consistency. As I said, alpha wouldn't get through the paper at all, so it'd be useless for this type of thing. And all of gamma would get through, so the reading wouldn't vary, also useless. We have to again use a source with a long half-life because it means less replacement and therefore less exposure to radioactive sources for us. And that's how we explain the different uses of radioactive sources.